Hey guys, Jenkins here again, and this week we're going to be talking about a completely new topic, something which you've probably seen before in real life, but don't have the scientific vocabulary to properly explain yet. At the end of this week, the goal is that you do. So we're going to be talking about something called, wait for it, waves. We're going to be talking about waves. So yeah, you've probably seen a depiction of a wave on some sort of media, like a TV show or a video game or something like that. You might have this vague idea of what a wave is, or you might be very sure that you know what a wave is because you've seen the ocean or something like that. And you're probably right. Those are all probably representations of waves. But today we're going to talk about what waves are, and what their characteristics are, and some of the distinct behaviors that they have. And it's very interesting. Waves are all around us. You're actually seeing me with waves right now. Light is a wave, right? So ocean waves, light is a wave, and you're hearing me through sound, which is also a wave. Now, these are all different types of waves. Those are three different types of waves. And I'm going to teach you how to tell the difference between all three of them. But let's go ahead and get some basics down. So what is a wave? A wave is nothing but a rhythmic disturbance in a medium. And what does that mean? A rhythmic disturbance? Well, a rhythm is, right? A wave has rhythm to it. And that rhythm is going to be decided by a couple things, right? So a wave's rhythm, we're going to call its frequency. Frequency, right? You might have heard that word as well, like a radio frequency. That's the same concept. It is the rhythm of this energy traveling through some medium, right? It's a frequency. How frequent something is how many times it occurs per unit of time. So waves, we're going to think about its frequency is how many times does the wave happen every second. And you can imagine a high frequency and a low frequency are very different. And I'm going to show you that. So I have here two tuning rods, right? One is a little guy, one's a big old guy. And these are going to produce different frequencies, right? Now, listen here. Frequency 1. Frequency 2. Oh. Frequency 1, frequency 2. So the frequency of a wave, when it comes to sound, determines what we call its pitch, right? And that's has a lot to do with singing and music, right? A higher frequency, and a lower frequency, ooh, right? It determines a lot of things in music. So high and low frequencies right there. What did I just do though? I had to hit that. Why did I have to hit it? Because I used some energy, right? And I put it into this fork and it's giving that energy off. Waves are just energy traveling through mediums like air or even water or even outer space. No medium at all. So that's its frequency, right? It's rhythm. And what does it go through? It goes through what we call, you might have heard this word too. It goes through a medium. No, not the thing that occurs between large and small, but a medium. Something that something goes through, right? And a medium could be anything. It could be air. It could be water. It could be even a solid. Waves go through when someone knocks at your door, the energy is going through the wood or the metal and into the air. It actually travels faster through the solid than it does through the air, right? And I'll show you how that works in just a second. But a medium is what the wave goes through. It's that simple, right? And the plural of medium, which means more than one, are media, right? And you definitely have seen this word because you've seen it in things like social media. Well, social media are just mediums through which information travels. So that's a very similar concept that we use outside of physics. But a medium is what a wave goes through, right? Now, let's talk about the parts of the wave. It's very important. I will draw a wave here and explain its different features as best as I can. So this would be an example of a wave, a specific type of wave, but a wave nonetheless. And I can see it's got some defining features, right? It's got this up and down nature. It's got a rhythm to it. I can snap every time it's at this equilibrium point and goes all the way up, all the way down, and all the way back up. That's one wave, right? And then another one right here. So there's two waves here, all the way up, all the way down, all the way back up. So if this occurs, right, over the span of 1 second, there's two waves in a second. Its frequency is 2, right? And we measure a wave's frequency, its frequency, in what we call hertz. And you've definitely heard this word before. And no, it's not the car rental company. It's a word called hertz, or abbreviated HZ, right? And that's the frequency of the wave. If you have ever messed with the dial on an old radio, it says frequency in hertz, right? Well, that's exactly what this is. That radio antenna is picking up these waves, right? And depending on the frequency, that'll depend on what it's tuned to, right? So we have the frequency of this wave, right? How many waves occur per second. You can see if this is 1 second that goes by, we have two waves. And remember, a wave starts at some point, right? Does a complete oscillation, does a up, down, back up, and returns from where it started. That's one wave. So you can see here that I have two waves. There's one wave. Now there's two waves. There's two waves. 2 waves in a second means I have a 2 hertz wave, a frequency of 2. This is a 2 hertz wave. Now, some other parts about it. How high it goes, right? So if this is the equilibrium point, this middle line, it goes up and it also goes down, right? Now, some waves don't go up that far, and some waves go up very far. This is called the amplitude. The amplitude, and I'll write that word here, amplitude. You might have seen a word similar to that if you've ever heard of an amplifier, right? Or ample, which means enough. The amplitude is the magnitude of this upward travel of the wave, right? And a really good analogy is like sound, right? The louder it is, the more amplitude it has. Now you might be fooled into thinking that the more frequency, the louder it is, but I can take this really high frequency tuning fork and make it really soft. I can take this low frequency and I can make it really loud. Amplitude has more to do with this upward motion rather than how many waves per second. It's frequency, it's pitch. It's how tall that is, right? Which corresponds to the amount of energy that you put in it, right? In the exercise that I have you do that's moving the wrench up and down to put a wave in a medium, you can see the higher you move that wrench and higher you fling it, the higher the amplitude of that wave does get, right? So we talked about the frequency, we've talked about the amplitude of the wave, how high it goes, right? And these are equal. How high it goes in the positive direction is the same as how low it goes in the negative direction. But we call these points at the very top of these, we call these crests. That's the crest of a wave, and this right here is the trough of a wave right there. The crest and the trough, right? So the high point is the crest, and the low point is the trough. You might have heard the word trough maybe. It's what a pig eats out of, right? Very low sort of word, right? It's down there. It's the trough. And up here is the crest of the mountain, right? But they're the same distance from the center line, right? And there's one more thing that you need to know about too. We talked about the frequency, right? The rhythm, how many waves per second. We talked about the amplitude, right? And we talked about crests and troughs. Now, the most important thing, I think, or one of the most important things, is how long a wave is, right? Which is very related to its frequency. But how long a wave is we measure it from one point to the very same point in another wave, in the same wave. So I can pick a point. I'm going to measure from a crest to a crest, right? Because that's one wave, going down all the way back up to the same point. And this distance is called something. It's called the, and I'm going to draw that straighter, it's called the wave length. It's called the wavelength. It's measured in meters or nanometers. It's a distance. It's an actual distance between waves. We can measure them. And that will determine a lot of things about them, where they are in the electromagnetic spectrum, which we'll talk about next week. But this is a wavelength. It's given a special Greek character, and that is lambda for L, right? So wavelength lambda. And how do I find that? It's actually very, very simple. I measure it, or I can use what's called the wave speed equation to figure it out. Now let's talk about that real quick. So this is the length of the wave, and of course it's going to dictate a whole bunch of stuff. Let me show you some examples of, maybe this is a long wavelength and this is a short wavelength wave. You can see that the distance between the crests are way different in these two waves. They're both waves, they're both rhythmic disturbances in a medium, but one has a very large distance between the crests and one has a very small distance. Now I could also pick troughs. It doesn't matter. I can just pick, I have to use the same reference point though in determining how long these waves are, right? So you can tell the longer the wavelength, right, the shorter the frequency. The shorter the wavelength, the bigger the frequency. This has a very short wavelength, but it's got a high frequency because they are inversely related. I'm going to show that to you with what's called the wave speed equation. Here's how I determine the speed of a wave. The speed of a wave, right? The speed of a wave, right, is equal to the frequency times lambda wavelength. So we can say the velocity, the speed of the wave, because they're definitely going to have a direction, is going to be equal to the frequency times the wavelength, right? So let's do a sample. If I have a wave that has a frequency of 2 hertz, and a wavelength of 10 meters, what would the speed be? It would be 2 times 10, 20 meters per second, right? Because my frequency measures time, right? And my wavelength measures distance. So I have meters and seconds, right? Meters and wavelength, seconds and frequency. I put those together and I get 20 meters per second. This is very useful in solving a bunch of problems. We can determine the speed of sound if we know the frequency of the sound and the wavelength of the sound. But this is the basics. I am going to show you some more stuff using my Slinky here in 1 second. But you can use all of this to go ahead and solve the equations that I have for you in the multiple choice section and answer the basic vocab. And I'll come right back out at you with some demonstrations of how these things actually move in real life. Be right back.